Okay, thank you. So we're on our way to proving that the critical 2-point function for the weakly self-avoiding walk behaves like 1 over x to the d minus 2 for dimensions higher than 4. And what we've accomplished so far is that we have the Lace expansion, which in Fourier language is saying that the Fourier transform of the 2-point function is given by this 1 over f hat, where f hat is the simple random walk part together with this more complicated function pi, which we have represented in terms of a sum of diagrams. And we introduced this bootstrap function somewhere. Here it is. It's the supremum over all x of gz of x divided by the critical free 2-point function, the simple random walk one. We know it's less than or equal to 1 if z is less than or equal to 1 over 2d. We know that b is continuous. And we know that if b is less than or equal to 3, we have an infrared bound. And we have pointwise bounds on pi, which imply continuity bounds for derivatives of the Fourier transform of pi. All right. So in terms of notation, we had this a mu, which was the given by this formula, the function on Z d. D is just the transition probability for the simple random walk. And then we had fz, which is 1 minus 2dz, d minus pi z. And these obey the equations a mu times c mu. C mu is the simple random walk 2-point function, is delta, and fz involved with gz is also delta. So now what I'm going to do is try to extract the exact leading behavior of the 2-point function, gz. So I'm going to give myself a parameter lambda here and another parameter mu. So lambda is anything at the moment, and mu is going to be in 0, 1 over 2d. And I'm going to write gz as lambda times c mu plus delta star gz minus lambda c mu star delta. So delta is the identity for convolution. So when I start with delta, nothing happens. And so this just says that g equals g, which we already knew. But I'm going to now replace these two deltas, these are delta zeros, by one or the other of these convolutions. So it's going to be c mu star a mu star gz. Convolution is commutative, minus lambda c mu star fz star gz. I'm just doing algebra here. And I'll write that as lambda c mu plus c mu star e, which depends on z, and lambda and mu star gz. And e is just what it has to be in order to make that true. So ez lambda mu is equal to a mu minus lambda fz. And now what I want to do, and this is really a key idea, this is like crucial, this point right here, is to pick the right lambda and mu. And I'm going to choose them in such a way that this E has vanishing 0th and second moments. Its first moment vanishes just by symmetry, so that I don't need to consider that one. So I'm going to choose lambda z and mu z, so they're going to depend on z. such that the sum over x of Ez lambda z mu z of x and the sum over x of x squared times Ez lambda z mu z of x is equal to 0. Now, why can I do that? It's just that these are just two linear equations in two unknowns. So you can solve these equations. And what you find is that lambda z is equal to 1 over fz hat 0 minus the sum over x of x squared fz of x. And mu z is equal to 2d mu z is equal to 1 minus lambda times fz hat of 0. Fz hat of 0 is just the reciprocal of the susceptibility. This looks negative, but actually this is greater than or equal to 0. There's also a minus sign inside the f. And so lambda z is greater than or equal to 0. This turns out to be inside 0, 1. It's not hard to check that, but I won't go through that right now. So moreover, if we have this bootstrap hypothesis, which is kind of starting to feel a little bit onerous right now, this hypothesis, because it's doing so much for us that maybe we're relying on something too much, but eventually we're going to see that it's true. So, but if it's true, then this is basically an expression in terms of pi. The d's cancel, and you find that lambda z equals 1 plus order beta. And that at ZC, where the susceptibility is infinite, its reciprocal is 0, mu ZC is the critical one for the simple random walk. So that choice of mu, that mu z, when z is critical, is actually the critical one also for the simple random walk. So with these choices, we see that Gz is equal to lambda z times c mu z plus fz, where what is f? Small f? It's the rest. So it's c mu z star e. Let me just call it now ez when the lambda is evaluated at lambda z and the mu is evaluated at mu z, everything only determined by z. So I'll write that as ez star gz. And what I want to claim is that when z is close to critical, this term has faster decay than the critical decay that we would see from c mu zc, okay, which is the 1 over x to the d minus 2, and that this is exactly the right amplitude to put in front of that. In order for the f to be smaller. We're really extracting the leading behavior there. And that argument is going to go through Fourier analysis, so it's important to notice that small f is the product, Fourier transform is the product of these Fourier transforms. And now we look at a consequence of the key idea and proposition 1. If we have our bootstrap hypothesis, then this E Ez, which has zeroth moment, zero first moment by symmetry, 0 second moment, 0 third moment by symmetry, will only have, it'll start with a fourth moment. And so in terms of its Fourier transform, that tells you that Ez hat of k is going to be bounded by, there's a beta that comes in because it's inside pi, which is inside E, and then you'll have k to the fourth. Right, the order k to the 0 term is just going to be the zeroth moment of E. The k squared term would be the second moment of E as coefficient. And they're not present, so we're not going to get the k to the fourth term. So what that means is that this Fz hat of k is bounded by a constant times, well, the C obeys an infrared bound all the way up to the critical point. So that C hat is going to be bounded by 1 over k squared. And then the E is bounded by beta times k to the fourth. And the G, which is 1 over F is bounded below by constant multiple of k to the fourth. That was the infrared bound that was part of the last conclusion of proposition 1. So we get another 1 over k squared here. So it's order beta times k to the 0, if you like. It's much better in terms of the behavior near k equals 0 than this term, which is like 1 over k squared when we get to the critical point. This one's blowing up. This one's not blowing up at all. So this is going to have worse x dependence than this one. In fact, you can take derivatives. So alpha is a multi-index here. I'm taking derivatives with respect to k. And so what happens, I'm not going to go through the details here, is each time you take a derivative, basically you lose a power of k. So you keep the beta, but you're going to have 1 over k to the alpha. And you'll be able to do this if alpha is less than or equal to d minus 2. That's how many derivatives you'll be able to take, basically because of this fact. I'm not going to do the arithmetic right now that says that this is the limiting factor, but this is for d equals 5, this is the best you can do. Right. So that means that this is integrable. Right? It's like integrable with room to spare. You have 1 over k to the d minus 2. That's integrable at k equals 0 in d dimensions. 1 over k to the d minus 1 would be bad. It wouldn't be integrable. 1 over k to the d minus 2 is fine. No, I guess 1 over d minus 1 would also be okay, but there's reasons why I can't take more derivatives than that. So these facts about F are actually pretty important. So first fact is that if you do integration by parts, you find that Fz of x is less than or equal to order beta over k to the alpha for those alphas, less than or equal to d minus 2. Right? Fz of x is equal to an integral. I guess I never wrote down the formula for the inverse Fourier transform, but maybe I should do that now. This is an x, thank you. Yeah, so fz of x is equal to the integral over minus pi to the d of fz hat of k e to the I k dot x dk over 2 pi to the d. So if I have derivatives acting here, then I can move them over to here. And when I apply them here, I get factors of x, and so I get my bound. And not only that, but this fact that this derivative is in L1 by the Riemann-Lebesgue lemma tells me that fz of x is little o of 1 over x to the d minus 2. And let me actually take the alpha, the best alpha I can take there, which is d minus 2. So I have, that's because once you have this, that's automatic by Riemann-Lebesgue. So I have two bounds here. One is quantitative in terms of the factor of beta, which is in the constant. The Riemann-Lebesgue lemma won't give me that, but it gives me something different, which is a little o, with no control over the beta dependence here. So those two facts just follow from this bound. Okay, so now I can come to proposition 2, which is where the bootstrap takes place. So let d be greater than 4, beta be small, and let z be something in between 1 over 2d and zc. And it doesn't matter about 1 over 2d, but so if b of z is less than or equal to 3, then b of z is less than or equal to 2. Looks funny, right? So it's saying that if you have a bad bound, that implies a better one. Well, the proof is pretty easy now. Just a few lines. So let's just write down what star tells us. This is star. These two statements tell me two things about the 2-point function, because g is lambda c plus f, and I know something about f. I know two things about f here. So by star, the Riemann-Lebesgue one tells me that gz of x is equal to lambda c c mu z of x plus little o of 1 over x to the d minus 2. And the integration by parts bound tells me that it's equal to lambda z c mu z of x plus big O of beta times 1 over x to the d minus 2. I leave out the 1 plus in the denominator, I think. It's not worth carrying around. Now, I claimed back here that, remember, we're assuming now that b of z is less than or equal to 3, so all of the consequences of proposition 1 are now hold. We know that they hold under this assumption, which I'm assuming. So in particular, I know that lambda is 1 plus order beta. So this is less than 1 plus order beta times c. And I take the worst mu z, which is 1 over 2d. Mu z was less than or equal to 1 over 2d. And this thing here is the asymptotic behavior of the critical simple random walk 2-point function. So up to a constant, I can replace this by C1 over 2D and just absorb that constant into the big O. So I'll get a big O of beta times C1 over 2D of x. And I'm missing some parentheses there. So now I take beta small enough that these two O of betas add up to less than 1. And then this is less than or equal to 2 times C1 over 2D x. And that's the statement that B of Z is less than or equal to 2, right? Because B of Z was defined to be the sup over x of GZ of x over C1 over 2dx. So that ratio is just bounded by 2 for every x. Okay, so that's the proof. Well, everything has been contingent on B of Z being less than or equal to 3, but now we'll be able to see that it actually is. So now we proved the theorem that I started with last hour. So the theorem said that the critical 2-point function is equal to 1 plus order beta times basically C1 over 2D of x plus little o of smaller remainder. So the proof is by picture, really. So here's the z-axis. Here's B of Z. Here's 1, 2, 3, 1 over 2D, ZC. So I want to draw the graph of B. So I know that for Z less than or equal to 1 over 2D, B is less than or equal to 1. That was one of the first observations that we made when the bootstrap function B of Z was defined. So the graph of B is doing something here. It stays less than or equal to 1. What about between 1 over 2D and ZC? Well, I know that B cannot be between 3 and 2. Because if it was 2.5, it would be less than or equal to 3, but greater than 2. So that's not allowed. So this region here is a forbidden region for the graph of B. But B is continuous. So its only other option is to stay below this line. And well, I mean, at this point, you can argue in various ways, but monotone convergence is going to be sufficient. So actually, what this says, by the picture, B of Z is less than or equal to 2 for all Z less than or equal to ZC. So it's also less than or equal to 3. So everything that we concluded under the bootstrap hypothesis that B of Z is less than or equal to 3 is now known to be true. Including this. So now we just let Z go to ZC in this equation, take Z equals ZC, we get the critical 2-point function, 1 plus order beta, we get the critical 2-point function for simple random walk here, and we have our smaller error. So all statements in proof of proposition 2 hold. So at ZC, we get that GZC of X is equal to lambda ZC, which is 1 plus order beta, C1 over 2D, because mu ZC was 1 over 2D, plus small o. And so that completes the proof. Any questions? So this proof generalizes in many ways. So in particular, as I mentioned earlier, it's been proved, the statement of the theorem has been proved for strictly self-avoiding walk in all dimensions greater than or equal to 5. The little o there can be replaced by big O of 1 over x to the d minus epsilon for any epsilon positive. It's been done for percolation in high dimensions, easing, many other models. So those are in papers with Yucheng Liu, one of which just appeared in AIHP, I think last week, 2 years after it was accepted for publication. And the other one is in PTRF in the Grimmett birthday volume. It was published in 2024 on the PTRF webpage. Yucheng Liu and Matthew Dixon have also done this in the continuum. So if with application to the random connection model in particular, there's a continuum version of this where instead of having functions on the lattice, you have functions on RD. So there are many things that come out of this. Now, I want to move on to part 2. So that was part 1, the critical decay. Part 2 is, there's one good brush.
By the way, Gordon.
Here it is.
Can.
Oh, is that right? Okay, because I was finding that this one, use the white part. Yeah, I think this is cleaner. No, it's yeah, you're right. It doesn't matter at this stage. The brushes need cleaning. Build them up with chalk.
Gordon?
Yes.
So in that, did you just use the big O of 1 over mod of x to the power d minus 2 was probably in that derivation?
I used both. So I used the big O with the beta in order to get the 2. But I used the Riemann-Lebesgue lemma to get the small O. So I needed both.
Sorry, I also have a question.
Yes.
You said this technique has also been used for the strictly self-avoiding walk.
Right.
In that case, what's the perturbative parameter? Here you have beta there. What do you use?
Yeah. So that's a whole story. It's 1 over d minus dc, so 1 over d minus 4. But when d is 5, that's not so small. So you have to work hard. It's a computer-assisted proof. Yeah. No, so that was there already in the 2003 paper with Remco van der Hofstadt and Takashi Hara. What's new is daring to take more derivatives. So in that work, we just took 2 derivatives or maybe a little bit more, a fractional derivative more. Here, I'm really using the full decay of the pi and taking this many derivatives and just realizing that bounds on this Fourier transform give you everything you need, because then the proof is very simple. And what we did in 2003 was in this C star E star G thing, we worked very hard on, I can't remember whether it was this factor or this one, on getting estimates of sort of pairwise. So there was really a lot of Fourier analysis involved in getting an estimate on a convolution like this and then doing the convolution with the other thing. So we missed something. All right, so now I want to move on to the subcritical behavior. And for any dimension greater than or equal to 2, it has exponential decay. So I mentioned that earlier when I was saying in the bootstrap function, the soup was attained because the numerator in the bootstrap function was decaying exponentially, the 2-point function. But let's just check that now. It's very easy. So if I have a subcritical z, and I look at gz of x, it's the sum n equals 0 to infinity, cn of x, z to the n. I'm thinking about strictly self-avoiding walk now. If you have a walk that goes from 0 to x in n steps, if x is far away, n has to be big. So the minimal number of steps that you can take are the infinity norm of x. You must take at least that many steps. And now if I take some z prime, which is halfway between z and zc, I can write this as the sum n equals x infinity to infinity. Actually, I'll just bound it now. I'll bound Cn of x just by Cn, feeling very generous. And then write z over z prime to the n times z prime to the n. So I've just multiplied, divided by z prime to the n, but the inequality is due to the fact that I just forgot about the fact that I was only considering walks that end at x. Now this z over z prime is less than 1. And I'm just going to take out the biggest factor that it can be. And then after I've done that, I'll just relax the sum over n to go all the way from 0 to infinity, and then I'll just have chi of z prime. The susceptibility, the generating function for the sequence Cn. And because z prime is finite, this is z over z prime. This is finite. This is less than 1. So I have exponential decay. Okay, easy. Now also, I have the following inequality. That if I look at gz of m plus n times E1, E1 is the unit vector in the one direction. This is less than or equal to the bubble diagram, which I'll define, times gz of NE1 times gz of ME1. No, sorry, I've got it the wrong way around. This product, NE1, ME1, is bounded like that. Why? So actually, you can replace E1 by any x. It would still be true. Let's do it for E1. So here's 0, here's NE1, here's n plus ME1. So this product here is a product over generating functions for self-avoiding walks that go from 0 to NE1 with ones that go from NE1 to ME1, n plus ME1, just by translation invariance. So then what I'll do is just notice that this is like a product. Oh yeah, what is B? B is the bubble diagram. It's the L2 norm squared of the 2-point function. And so pictorially, it's this, where this is summed over. So here, if I take the last time that the red walk hits the blue walk, then this green walk that I'm drawing will be self-avoiding. And it'll be a self-avoiding walk that goes from 0 to n plus m e1. That's where this factor comes from. Then in this factor, we've got, a self-avoiding walk that goes from n e1 to somewhere, and a blue one that goes from n e1 to that same place. And they may be intersecting themselves many times, but they're each individually self-avoiding, and so that's where the bubble comes from. Okay, so in the bubble, it's like the origin corresponds to this point in the bubble, and the point that's summed is this one. So we have that bound, and that immediately implies, by a subadditivity argument, that the following limit exists. mze1 is equal to the limit, as n goes to infinity, of minus the logarithm of gz of ne1 divided by n. This limit exists. And various things are known about this limit. As z goes to 0, m goes to infinity. So, I mean, these require arguments, which I'm not going to present, but. And mze1, that one's easy to prove. This one's hard to prove. That as z approaches the critical value, m goes to 0. Yes? Yeah, yeah. So as I said, you could replace this E1 by any x. It would just sort of rotate this thing, and you'd get a mass that depends on x. So that would, its reciprocal would be the correlation length. Yeah, good question. So I'm coming to that. That is basically the almost the entire topic of what I'm going to be discussing for the rest of today and tomorrow. More refined version of your question, but exactly that. And so here's a theorem that addresses your issue. It was first proved by Chase and Chase. It was published in 886, long ago now. And it was for the case of on-axis two-point function, like I've got here. But then Dima Yoffe in 1998 took it off axis, so to all directions. So this is for the strictly self-avoiding walk. It says that for d greater than or equal to 2, there's no high dimension hypothesis here. For z any number between 0 and zc, there exists a norm on Rd that depends on z. Actually, that norm is something in between the infinity norm and the one norm, such that gz of x is asymptotic as x goes to infinity to some constant that depends on z and the direction of x. So the unit vector pointing in the direction of x, I'll denote by x hat, times 1 over the norm. Actually, here you could put any norm, but let me put this one, d minus 1 over 2, e to the minus mz of e1 times the z norm of x. Yeah. And this decay is what's known as Ornstein Zernike decay. So you have the exponential decay, but what really makes it Ornstein Zernike is this 1 over x to the d minus 1 over 2. This power d minus 1 over 2 is sort of the hallmark of Ornstein Zernike decay. Now, this type of theorem has been proved for many models. Percolation, it was proved shortly afterwards, I think in 1990 maybe, by Alexander Chase and Chase, or Campanino Chase and Chase. There were a bunch of papers with Campanino. There are many papers with Velenik and Yaffe and co-authors. We're going to hear next week, Luca Dallimont is going to talk about this in FK models. So this Ornstein Zernike decay is sort of everywhere. It's in Ising and many other models. And there's something curious about it when you first look at it, at least to me, that puzzled me at first, which is, wait a minute, the mass should be 0 at the critical point, but the power is wrong, right? If you just erase this, you have the wrong power. You have 1 over x to the d minus 1 over 2 when we just saw that the correct power is 1 over x to the d minus 2. They're different. Well, for d equals 3, they're the same, but that's kind of a fluke. They're different. And so this is not properly describing what's happening in the joint limit as x goes to infinity and as z goes to zc. In other words, this c has to be doing something dramatic as z goes to zc. And this project that I've been working on with Yucheng Liu is all about that. And it began with an earlier paper that was published in Alea, I think in 2023, with my former PhD student, Emmanuel Mishta, where we examined the decay of the massive green function for simple random walk. So what I called before CZ of x. And we used the fact that that green function can be represented by a one-dimensional integral of a product of modified Bessel functions of the first kind. And using properties of Bessel functions, we could then calculate the asymptotics. And so we figured out what was going on there. That was not completely satisfactory because as soon as you change the model a little bit, you don't longer have the representation in terms of modified Bessel functions. And so, what are you going to do? So with Yucheng, we did something different. And that's what I want to talk about. Okay, so this is posing now for us a question about the compatibility of critical and Ornstein Zernike decay. How can we understand that? And that brings us to the notion of Ornstein Zernike equation. So the OZ equation, which was first studied in the context of the theory of fluids and statistical mechanics by Ornstein and Zernike, I think in 1916, long ago, more than a century ago. They wrote down an equation in their context, which actually shows up in many other contexts, and it's this equation. G equals delta plus J star G. So in our setup, this J for simple random walk, for example, would be what I call 2 times the dimension times capital D, the transition probability for simple random walk. It's something that you know. And what you want to know is if I, depending on what J I put in here, what is going to be the decay of this G for large values of X. And in fact, Ornstein and Zernike did not have a delta here. They had some other function. So you can put in some other function H. And that's okay in our theory with Yucheng. We also have that. So this is, but let's not complicate life too much. Let's keep it simple with the delta for the rest of the course. And so the examples that we have 2 examples already. I talked about simple random walk before, but we could take a more general random walk. So we could take P of X to be, just the probability distribution starting from 0 that our simple random walk steps from 0 to X in its first step, and define Gz of X to be the green function, the massive green function. So that would be the sum n equals 0 to infinity, Zn P, the n-fold convolution of P evaluated at X. That's the n-step transition probability to go from 0 to X, that convolution. So this one obeys Gz is equal to delta 0 plus P, I guess, plus Zp star G. So that's the OZ equation with J equal to Z times P. And in our analysis, the Fourier plays a big role again. So it's maybe worth mentioning that this G would have a Fourier transform, which is 1 over 1 minus Zp hat. Okay. And I'll write down the inverse Fourier transform again, because that's going to be important for us. So we'll want to be going back and forth between the Fourier and the X-space representation. And I'll just finish up by mentioning the last example, the second example. So self-avoiding walk for d greater than 4, where we have the control of pi. So we have Gz is equal to delta 0 plus, I'm going to change in the second half of the course, what used to be called 2dz will now be called z. I want the critical value to be 1, close to 1 rather than 2d. So it will be, and that's the case here too. So it'll be z times p plus pi z star Gz. So now the J is much more complicated than it was before because it has the pi inside it. But we know a lot about pi now. We know how to bound pi. So that's using the Lace expansion. So that's the OZ equation. And this time Gz of k. I mean, I'm repeating myself here, but maybe the 2D factor is a little bit different. So it's worth writing it down. And Gz of x is equal to the integral minus pi to the d, writing out explicitly what the denominator is, what I called f before. So we know a lot about pi. We know everything about p hat. We know a lot about pi hat. And the idea is that we want to use our knowledge in order to do this integral, basically, or at least compute the large X behavior of that integral. So that's what I want to do. And just to finish up, I'll write down what the generic equation that we have with the Z parameter is. So the generic equation is an equation Gz equals delta 0 minus Jz star Gz. And it's a plus. And two things to note that are important. First one is that J, okay, I'm going to stop. Jz can be negative. It's not a probability distribution necessarily. Because this P is supported on neighbors, if we're talking about nearest neighbor model on neighbors of 0. Pi is long range and it can be negative. The first term in pi, in that sum of diagrams came in with a minus sign. So pi can be negative, so we can't use probability theory. And the second thing is that J can be long range. It can be infinite range. Pi of x could be non-zero for any x, no matter how big it is. Okay, so I'll stop here, and tomorrow morning I'm going to prove a theorem like this in the generic situation that tells you what this C is doing as Z approaches that C. Okay. Thank you.
Questions in line or in us?
Hello, can you hear me? Yes. So my first, thank you for the lecture. I'm looking forward to see the proof. So my question is, if I anticipate a little bit, those proofs of Chase and Yoffé, the Ornstein Zernike equation that arises is a bit more natural. It's in terms of those
Irreducible.
exactly irreducible parts and the bridge
Right.
decompose it that way. So can your method be applied to treat this specific Ornstein Zernike equation, or do you need this equation that is given by the less expansion to get this?
So we have not tried to put their framework into ours. That's an interesting thing that had occurred to me as well, that we might try to do. But the theorem that we prove says that if this J is in a nice function space, then everything's good, okay? So it wouldn't be so hard to check whether their J is in that category or not, but we just haven't done that. I mean, actually, now that I think of it, their theorem works for any D greater than 2. Our theorem will not for self-avoiding walk, because one of the outputs of the theory will be 1 over x to the d minus 2 decay at the critical point, which is not going to be true in low dimensions, even though we don't know how to prove that. So I'd like to look at what breaks there, but I think there's something that breaks.
Any other questions? Yeah, sure.
Hello. Yes, it's a more anecdotic question, but in the self-avoiding walk model, is it known that the norm that is introduced in the theorem about this Ornstein-Zernike decay is not the L2 norm when this is subcritical?
Yeah, so that's an interesting question. So in this generic setup that we're working in, we have a formula for the norm. So in principle, you can compute the norm. And for some random walks, we have computed the norm. Like, for example, for simple random walk, the norm changes monotonically from z equals 0 to z equals zc, which is 1 in this parameterization, from the L1 norm to the L2 norm. So you see the onset of Euclidean invariance at the critical point, which is not present at any subcritical value. So we haven't actually done a computation like this, but what our formula, I believe, would allow us to do is to, at least in the perturbative case for the weakly self-avoiding walk, to see how the distortion of the simple random walk norm occurs due to the presence of the small beta. Yeah. Yeah, I mean, in general, the computation of these norms is complicated. They're given by a variational, it's given by a variational principle. So we can prove various properties of it. For example, one thing that we prove, I'm telling you things that I wanted to say tomorrow, but the norm in that case, when J obeys the properties sort of uniformly for Z near ZC, will always converge to the Euclidean norm as Z approaches ZC. So that's like general without any additional input. But what happens away from ZC is complicated. We have proved that for any random walk with finite range, that as Z approaches 0, the norm, the unit ball of the norm approaches the convex hull of the support of the measure, the support of the step distribution. Yeah. And it's not monotone as Z approaches ZC in some examples.
So I have one naive question.
Yeah.
But it's more, I'm more like thinking of easing. So easing, there is Ornstein Zernike, right?
Yeah,
Correct.
right.
So suppose you're in the supercritical and you take the plus measure and you look at truncated correlations.
Mhm.
So these decay exponentially.
Right.
Do you expect like an Ornstein Zernike for these kind of things in the supercritical?
Yeah, so I think in the paper by Alexander Chase and Chase, which is for percolation, that that they see that. So I don't know if it's been done for easing, but
Any other questions? If not, then let's thank Gordon again. I have just 3 things, but I may forget one of them. So the first one is we're finalizing the schedule for next week. So we're going to send out an email with a preliminary one tomorrow. If you have any objections, then email back. If you don't have any objections, then don't email. The second thing is Ioan Malescu won't be here in person, so he's giving online lectures. There's no change to his timing tomorrow, but on Friday, they'll be a bit later, so 11:30 and 2:15. And the final third thing is that we scrapped the PhD talks because I think no one volunteered. So, but if you have any, oh yeah, fourth thing. So we have an open problem session on Monday in the Swiss style. So you know, anyone can give it, and I encourage everyone to think of something. So you know, start thinking of something gently now. Okay, great, thanks.